Hello, Shahab Ahmad welcomes you on the channel Define Mediocrity. The target part today is to cover all the concepts that are necessary for MDCAT in the chapter of gases. So we will cover gas laws like Boyle's, Charles, and Avogadro's, and we will cover all the units about pressure, temperature, their conversions. We'll make it easy, the units of R, and then we will go on and discuss ideal and non-ideal behavior of gases. We'll also discuss KMT, that is Kinetic Molecular Theory. So uh, let's do it. The first thing is, let's discuss pressure. What is pressure? Here I'm supposing a box. Okay, I have some particles in it. They are in random motion, but one thing is they go in a straight line till they bounce to something. So these particles moves in a straight line. This one too, this one too, all of them. So when they bounce, when they reach their destiny, their to the wall of the container is containing them. It is not allowing them to go out. Okay, here it reaches. What it does, it applies a force on this wall. This one too, all of them. Okay, so this force, which is applied by this tiny particle, I call it molecule. This force applied by this tiny particle, like the sum of them per unit area, is called pressure. Okay, the force that is applied by these tiny particles on the wall of this container, on the wall of my box, I call this force pressure. Okay, so now come to the physics of this pressure. What are the units of this pressure? This pressure could have the units as force, have the unit of Newton, and what is the unit of area? That is meter squared. So it is in denominator, I'll put minus in the power of 2. Okay, so one of its unit is Newton per meter squared. Okay, are there any other units for this pressure? Can we measure pressure in other units? Yes, we do. And that is, we measure it in atms, atmospheres. We measure it in torrs. We measure it in millimeter of Hgs. We measure it in bars. Okay, so all these are different units for for our pressure. Okay, so what is the relation between Newton meter, atms, torrs, millimeter of Hgs, bars? How are they related to one another? And I must tell you that 1 atm equals 760 torrs. Okay, and that those 760 torrs are equal 760 millimeter of Hgs. Means one torr equals 1 millimeter of Hg, and 1 atm equals 760 uh, millimeter of Hgs. And this is also equals 1.1325 bars. Okay, so this is the relation between atm, torrs, millimeter of Hg, and bar. But we did not talk about Newton per meter square. So 10, 13, 25 Newton per meter square, which are also called pascals. Okay, presented by the scientist, a very brilliant scientist named Pascal. So 10, 13, 25 Newton per meter squares or pascals equal 1 atm. So 1 atmosphere of pressure equals 10, 13, 25 pascals or 760 torrs or 760 millimeter of Hgs or 1.1325 0.01325 bars. So this is the relation between the units, and it was necessary for me to clarify this before I go forward and discuss other laws of gases, etc. So this was about pressure. So now we are done with pressure of the gas. We now the concept of pressure, we now know the units of pressure. Now we will go forward and discuss temperature. Okay, so what is temperature? We we said the degree of hotness or coldness of a body is called temperature. And it is also the average kinetic energy of the molecules. Okay, absolute temperature, there is a relation between absolute temperature and average kinetic energy of the molecules, direct relation. So this degree of hotness or coldness, what is it measured in? It is measured in different units. One of them is Celsius, that is a scale. The other one is Kelvin, the other one is Fahrenheit. Okay, so what are the relations between all of them? How is Celsius related to Kelvin and Kelvin to Fahrenheit or Celsius to Fahrenheit? Now, the relation between Kelvin and Celsius is if you were given temperature in Kelvin scale, you must add 273 to that temperature and you will get that temperature in your Kelvin scale. Suppose you were given 25 degrees in Celsius. So how much would that be in Kelvin? You must add 25 to 273 and you will get 2, 9 and 8 Kelvin. So 25 degrees equal to 98 Kelvin. Okay, what is the relation between Fahrenheit and Celsius then? It is very simple. Fahrenheit equals 9C. You must remember 9C over 5 plus 32. What is C? C is the temperature in Celsius scale. So if Celsius scale temperature is given, you can convert it into Fahrenheit. Very easy peasy. Okay, there is one temperature uh, that is equal both in Fahrenheit and Celsius. That is, I must give you it. It is minus 40 degrees C. So if temperature is minus 40 degrees, it will be equal both in Fahrenheit and Celsius. We can do the calculation. Suppose I were to put minus 40 degrees in Celsius in this equation. F equals 9 into minus 40 over 5 plus 32. Okay, 9 4 36, so 360 over 5 equals F plus 32. So 5 7 35 10 5 to 10. So from this side I'm getting minus 72 minus 72 plus 32. I'm getting in Fahrenheit. This temperature is minus 40 Fahrenheit. So which means if I took minus 40 in Celsius, it is also equal to minus 40 in Fahrenheit. So this was a bit about temperature. Now we will go on and discuss volume, okay, and its units. So volume is the measure of space in 3 dimensions. Okay, in 1 dimension, when we measure space, it is called length. Okay, if we were to measure it in 3 dimension, what would we do? We will take length multiply length multiply length. Okay, that would be our thing to do. So length A multiply length B multiply length C. Okay, so this will give me the whole space, the three-dimensional space that is included in this. Okay, so means length over length over length, which means if I know the unit of length, I can find the unit of volume. So suppose I'm taking the unit of length is meter. So then meter over multiply meter, I'm getting meter cube becomes the unit of volume. There are other units of length too, that is decimeter, that is centimeter. Okay, so if I were to take the unit of volume in decimeters and centimeters, it would become decimeter cube and centimeter cube. To decimeter cube, I also call liter. It is 1 decimeter cube equals 1 liter, and 1 centimeter cube equals 1 milliliter. Okay. Now, what is the conversion between meters and centimeters and meters and decimeters and centimeter and decimeters? So what is the conversion factor between them? First of all, let's find the conversion factor between meters and decimeters. So I know that 1 decimeter cube equals 1 decimeter cube. This is clear and cut, very obvious to write this. Okay, but now I'll do something. As this cube is both on DC and meter, so this hand side remains the same, and I am going to temper this side. What am I gonna put instead of DC? DC equal 10 to power minus 1. So instead of 1 multiplied 10 to power minus 1 becomes 1 multiplied 10 to power minus 1. And meter remains in its place. And I must take the cube of the whole. Okay. This cube is not on this one. I must bring it out. But there is nothing changes if I bring it out or not. Okay. But the point is, I am taking the cube on both DC and meter. So 1 decimeter cube becomes equal to 1 power 3. Okay, there are 2 powers. So if this is the rule of mathematics, 2 powers multiply with each other. So minus 1 multiply with 3, what will I get? I'll get 1 multiply 10 to power minus 3 meter, and m power cube will come in its place. So 1 decimeter cube becomes equal to 1 multiply 10 to power minus 3 meter cube. That is 10 to power minus 3 meter cube. So we must remember this relationship. At 1 decimeter, now we can also calculate it. If I did not know the relationship between decimeter, now we know the relation between decimeter cube and meter cube. What is the relation between centimeter cube and meter cube? So again, I'll start with the same thing. That is 1 centimeter cube equals 1 centimeter cube. Again, what I'll do is this left hand side remains the same. I'll take the cube on centi. Centi equals 10 to power minus 2, and meter, I'll take the cube on both. This becomes 1 centimeter cube equals 10 to power minus 6 meter cube. Now, I have to relate centimeter cube and centimeter cube and decimeter cube. What can I do? It is easy. We can do a bit of mathematics and relate them both. Okay. Let's divide centimeter cube by decimeter cube. Okay. Let's divide this whole equation by this equation. Okay, that is, I must write this first. 1 centimeter cube equals 10 to power minus 6 meter cube. Okay, now I'll divide it by this equation. That is, divide 1 decimeter cube over 10 to power minus 3 meter cube. Okay, now easy peasy calculations. Meter cube goes with meter cube. Now this 10 to power minus 3 in denominator. Okay, so 3 goes with 6. So 2, if I were to take this denominator to numerator, this minus would become plus. So base is the same, and when I add, now powers could be added. Okay, so minus 6 and this minus 3 goes up, it becomes plus 3, and here I'm getting 1 centimeter cube or 1 decimeter cube. Okay, so now minus x plus 3, easy calculation, 10 to power minus 3. Okay, so 1 centimeter cube is equal. Now I can take this decimeter cube to that side of the equation, and here it is in division, to that side this becomes in multiplication. So this becomes decimeter cube. Okay, so it was not that difficult. We now relate 1 centimeter cube equals 10 to power minus 3 decimeter cube. Are you getting it or not? 1 centimeter cube is equal to 10 to power minus 3 deci and meter and cubes. Now, what will be the relation? What will be 1 decimeter cube equals? So, what can I do for that? I can divide both sides or multiply both sides by 10 to power plus 3. Okay, if I multiply both sides by 10 to power plus 3, what will I get? I will get 10 to power 3 centimeter cubes equals 10 to power minus 3, and here plus 3 decimeter cube, and here I'll guess 10 to power 3 centimeter cube equals 1 decimeter cube. Okay, so now I know the relation. You must remember this, and we will need this conversion. That 1 decimeter cube equals 10 to power 3 centimeter cubes. Okay, now we are done with the preliminary, we are done with the discussion of the quantities we'll need, that is pressure. We also now know the relation between the pressure terms, the units like the torrs and the millimeter of Hgs and pascals and etc in bars. And then we discussed the temperature and the conversions about temperature. Then we discussed a lot about the volumes. Now, what is the relation between, like now we will relate two of the quantities one by one. Okay, so now just let's relate pressure and volume. What is the relation between the pressure of a gas and its volume? You might have observed this, and this was observed also by Boyles. Now, we will come to Boyles later, but let's talk common sense, okay? Here I have some gas particles, suppose, and they are bumping into the walls of the container with some force. Okay, they are occupying some space to which I call volume. Okay, and they, with the force per unit area, I call pressure is here, it is P1. Now, suppose the same particles, number of particles, I must count them 2, 4, 6, 7, 8. Now, these particles have little space than they were in the previous case, like in this case. Now, what happens to the force? What happens to the frequency of the vibration, the frequency of collision? As now they don't have lots of space to cover, to bounce to the wall of the container. Okay, and they are congested in little space than they were in the previous case. The volume, I have shrunk it down. What happens is commonsensically, what happens to the pressure? The pressure will absolutely, with no doubt, the pressure will increase. Okay, so now this is V2 and we will have P2. So what am I getting? I am getting commonsensically that here, if I had a V1, volume V1, I had a certain pressure P1. Now, if I have decreased the volume, the pressure have increased. So somehow I can know that the product of both these quantities, like if I were to multiply P1 with V1, it must have been equal to P2 V2. Okay, somehow, because as I decreased the volume, the pressure increased. So both are, if I multiply them together, I'm getting the same quantity as in the first case. So this was put forward by Boyles. He said that his observation was in 1600s, and uh, I remember a story from my grandfather, and he said that it was a person observing some kind of increase in pressure with the help of or with the help of a bottle. He was pushing some smoke into the bottle. At the end, the the cork with which the bottle was closing, it burst open, like it was pushed outward because of the increase in pressure in the bottle from the smoke. And this was the idea for developing a piston, an engine, that is the heat engine of a train. So this was a story. Okay, so the increase, what happens, the increase in pressure will will push the volume outward. So this was a commonsensical observation put forward first by Boyles, so we must take his name. He said that there is an inverse relation between the pressure and volume of a gas. So if you were to increase the pressure of a gas, its volume expands, and if you contract the gas with increasing, you will be increasing pressure because you are contracting, you are decreasing the volume of the gas. Okay, so this was presented in this beautiful equation by Boyles. He said that there is an inverse relation between pressure and volume of a gas. In other words, he said that pressure and volume remains constant. The product of pressure and volume is a constant value. That is, he said that if you were to increase one of these quantities, the other will decrease. And as a result, you will have a straight line. If you were to plot a graph of Vp versus P or V, you would get a straight line, no curves whatsoever in the graph, because the product remains the same. As you are increasing the pressure, the volume decreases, and as a result, the products remain the same. There are other ways to plot a graph for the pressure and volume. So suppose you were to plot a graph, pressure versus volume, what would you get? You would get a parabola. Okay. All he was doing in this case, he was not changing the amount of substance, the amount of gas was constant. Okay, in temperature too. So in all these calculations, he made sure that the amount of substance in temperature of the gas remained constant. So temperature was constant, and also number of moles. There were two, a constant value. So now, what will be the ratio? What will be the relation between pressure and volume, one mole volume? If you were to plot a graph of pressure versus one mole volume, you will get a straight line, because there is the direct relation between the inverse of the volume. As we can see, the inverse of pressure is directly proportional to volume. Same is the case, the inverse of pressure is inversely proportional to directly proportional to the volume. The inverse of volume is directly proportional to pressure. This is common sense, okay? As you are increasing as you are increasing inverse of the volume, this means you are decreasing the volume. The increase in inverse means decrease in the volume, okay? So as you are decreasing the volume, the pressure increases. As you are increasing the pressure, inverse of the volume decreases, okay? So this is about the graphs. We could also plot the graph of the log of the quantities, okay? Is suppose we have PV equals constant K, okay? Now if I were to take log of these equations, log of P would be equal to log of V log of K. Now if I take this term to the other side of the equation, this becomes negative. So log of P equals log of K minus log of V. So this becomes a straight line equation. Y is equal to mx plus c. This is c. Okay. Now if I were to plot the graph of this, it's become like this with negative slope. Is here the slope is -1. Okay. And what is this equals to log of k, the c term, log of k. Okay. And on the y-axis, I must draw the graph over here for more clarity. This is my slope, which is -1, and this is the c from here to here, intercept, that is log of k. Okay. And what is on the x-axis? On the x-axis, I am getting log of v, and on the y-axis, I am getting log of p. Okay. And log of k is the y-intercept, and the slope is -1. So the downward slope of this graph uh, shows us that the pressure and volume are in inverse relation. Now if to this line, what I call this isotherm. Why I call this isotherm? Because I have taken the reading at constant temperature, and iso means same and term means temperature. All this reading was taken at same temperature. Now again, if I take it at another temperature, I'll have another curve, and at another temperature, another curve. Okay. Now, suppose I call this T1, this one T2, and this one T3. What is the relationship between T1, T2, and T3? For that, I have to draw a parallel to any of a perpendicular and a parallel to any of the axes. Suppose I am drawing a perpendicular to this axis. Okay, this perpendicular. Sorry, I have to correct it. So this is a perpendicular to my y-axis. That is the pressure. Now, I will draw a perpendicular to the x-axis and find out. So here, this is suppose V3, and here I am getting V2, and here I am getting V1. So what I got is that, I'll write it over here. I got that V3 is greater than V2 is greater than V1. Can't you see it? Here, look at this. As on this axis, the volume is increasing. So V3 is higher volume than V2 and then V1. So what about the temperatures then? Is T3 greater than T2 than T1? Yes. T3 is greater than T2 is greater than T1. And This was observed by a balloonist called whose name is Jacques Charles. So Charles in 1787 saw this relationship that his balloons in the morning were a bit placid than his balloons in the afternoon. Okay, noon and afternoon time when the sun was rising and the atmosphere was getting warmer, his balloons would have greater volume than in the morning or in the evening later. So he observed this, but never published his observation in any paper or journal. Later, Lucek published his thesis and gave credit to him. So we are seeing that for a greater temperature, the volume increases if the pressure remains constant. And how is the pressure to remain constant? The, the expansion of the balloon was allowing the pressure to remain constant as the balloon was giving more space to the particles when they were vibrating with higher speed. So we will talk about that now. Charles' law. Charles observed that the volume and temperature of a gas were in direct relations. So as you increase the temperature of a gas at constant pressure, you will see the expansion of the gas. This was an observation from the daily life. Okay, so Charles. Now we are into Charles. Sorry. Charles saw that the volume of a gas was in direct relation with the temperature of a gas. The greater the temperature, the greater would be the volume. Okay, so he saw the rise and fall of the volume with respect to temperature as we could plot a graph. Okay, volume versus temperature. As you increase the temperature, the volume increases. So we can also say that V over T is equal to K, or V1 over T1 is equal to V2 over T2. Now you can plot the other graphs for yourself by yourself. And that is if I were to plot a graph V over T versus V or T, any of that, I will find a straight line parallel to the axis. And now you can tell me to what this graph, this slope we call this isobar. Why we call this isobar? Because the readings must be taken at constant pressure. Iso means same and bar means pressure. So the readings must be at constant pressure. So this is also called isobar. Now you can plot other graphs by yourself. What will be the isobar if I were to increase the pressure, or will it be above this or below this? You must draw those and let me know in the comments. Okay, if you were given V1, T1 or and V2, you can find T2. Suppose this is very easy peasy. You must take the temperature in Kelvin scales and do the calculations. Very easy. But the Charles law, the Charles observations were then worked on by Kelvin, though he was very involved in the Karnaugh cycle and Clausius. Uh, but the same thing, the same observation is the expansion of the gas or compression of the gas with respect to temperature change. He observed that if we were to increase the temperature of a gas by 1 degree of Celsius, we will see that the volume of the gas change by by 273 of the original volume. So suppose I had the original volume of V naught. This would expand by 273, okay, 273 of the original volume per degree rise or fall in temperature. So if you were to find the final volume, you must add or subtract this this much, this change in the volume. Okay, so if we were to go into the details of this, suppose I were to change the temperature from 0 Celsius to minus 273, what would I get? I will get, suppose the temperature delta T equals minus 273. I got into minus 273 of Celsius scale. So what will I get? Though, let's see the change in the volume. This was the initial volume. I am finding what is the final volume. Okay, we final. So this is the initial volume we not. And I will see the change in the volume, original volume by 273 of the temperature. So now the temperature is minus 273. So what will I do is to multiply 273 with this term minus. Okay, this is very easy. This goes away with this. And I'm getting minus 1 multiplied with this plus. So minus 1 multiplied with the V naught, I get the equation is V naught minus V naught. Simple mathematics. So V final would become 0. So at minus 273 degrees, I will have no volume whatsoever of a gas. And to this temperature, minus 273 degrees Celsius, I call this absolute zero. Absolute zero. And this is the zero of the Kelvin scale. Okay, the Kelvin starts 0 from minus 273 degrees Celsius. And at this temperature, there is no motion of the molecules. Now, we will go forward and discuss one more law uh, about the relations of the quantities of gases. Okay. Now, that law is about the quantity of the gas, like the moles of the gas, number of particles of the gas, and the volume occupied by the gas. So this is commonsensical. If you blow a balloon, it increases in size. If you pump a tire, it increases in size. Why it increases in size? Because you're pushing the air into the tube or into the tire or into the balloon. So if you are putting more gas particle into the balloon or tire, it expands. What does this mean? The volume of the gas increases when you increase the number of particles of the gas in that volume. Okay, it expands. So this was an observation done by a scientist called Avogadro. Though his law was not this, he stated that for equal volumes at constant temperature and pressure, you will see that equal volume of gas contain equal number of particles. He said again, he said that for at constant temperature and pressure, at certain temperature and pressure, equal volume of a gas occupies equal number of particles of a gas. So this was his observations. Okay, and from that we have now derived Avogadro's numbers and also the volume occupied by gas at STP. So we have now come up with numerical values to his statement, but we will go to that later. First of all, he said that volume of a gas is directly proportional to number of moles of a gas. Greater the number of moles, greater will be its volume. So V1 over N is equal to K, or V1 over N1 is equal to V2 over N2. if we were to plot a graph, then you would see a straight line. Starting from the curve at 0, you will have no volume. For 0 number of moles, you have no volume. As you increase the number of particles, the volume of the gas increases. Okay, so he said that like now we know in numerical values that 1 mole of every gas independent of the gas occupies 22.4 decimeter cubes. Okay, independent of the gas, but you must take this calculation at STP, standard temperature and pressure. What is standard temperature? Standard temperature is 273.15 Kelvin. What is standard pressure? ST. And SP, what is standard pressure? That is 1 atm. So at standard temperature and standard pressure, you will observe that 1 mole of every gas occupies 22.4 decimeter cubes. We have solved some numericals with the help of this, which are present on our channel. You can watch it. But here we will go forward and now combine all these laws we discussed, Boyle's, Charles, and Avogadro's, and make a general equation out of all these laws and one constant for all these laws in combination. So all these laws were explaining just one behavior of the gas. That is, one was saying that volume of a gas is inversely proportional to pressure. The other was saying that volume of a gas is directly proportional to temperature. The other was saying that volume of a gas is directly proportional to number of moles. So if I were to combine, put a constant, or I were to combine them with a proportionality, I would see that inversely proportional to pressure, directly proportional to temperature, and directly proportional to number of moles. So I would get V directly proportional to temperature and number of moles and inversely proportional to pressure. Now here I am putting a constant in, that constant I am calling R. This is R. So R, T, and N over P. So if I were to take this P to this side of the equation, this would become PV equals nRT, as you remember it. Okay, so this becomes general gas equation or ideal gas equation. So we will go to the detail of R, but later. First of all, what can I do? I can find different things with the help of this. If I know pressure and volume, in temperature, I can find number of moles. If 3 of them are given, I can find the 4th one. Okay, this is with the help of this equation. Now, I can also find the density of a gas with the help of this equation. Okay, but we will go to that later. First of all, let's discuss R. Okay, so what is R? Now I will write PV equals nRT. Okay, I can find R if I put these N and T in denominator of the equation. So PV would become N over T is equal to R. So just a few moments earlier, we discussed that 1 mole of every gas occupies 22.4 decimeter cube at standard temperature and standard pressure. Okay, now if I were to put all these values, I can find the value of R. Here, let's do it. What is pressure? The value of pressure. The value of pressure is 1 atm. 1 atm. What is the value of volume? 22.4 dc in meter cube. Okay, what is the value of moles? That is one mole. And what is the value of temperature? That is 273 Kelvin. Now I can find the value of R for every gas. Okay, is Avogadro said that it is independent of the nature of the gas. Okay, so what can I do is divide here. This dot means multiply. Okay, so if I were to divide 22 by 273, I would get 0.0821. And now listen and look at the values of the units carefully. 0.082 atm dot decimeter cube, dot means multiply, dot per mole, as this mole is denominator. If it goes upward, it becomes per mole, and per Kelvin becomes the value of R. Okay, we learned a lots of values of lots of different units for pressure and for volume. So we can plug those values in and find out that the value of R changes. So R, if I were to take pressure instead of ATM in torrs, so 1 ATM was equal to 760 torrs. Now I can replace 1 ATM with 760 torrs here in this case, and 760 multiply with the 0.082. I will get 62.4 torr. Okay, I replaced ATM with torr, decimeter cube per mole per Kelvin. Okay, now if I were to replace decimeter cube with centimeter cube, how would I replace it? As just few moments earlier we did the calculations that 1 decimeter cube was equal to 10 to power 3 centimeter cubes. So I can put the value of it here in this equation, and I will see 1000 multiply with my answer, and I will see R equals 62400 torr centimeter cube, as I replaced it, this meter cube with centimeter cube, per mole in per Kelvin. Now, what about the value of R in system international units? That is Newton per meter squared in meter cube. If I replace torrs here, we will have the same value. If torr was of Hg, as torr and of Hg are the same, of Hg. Okay. Now, if I were to take the value of R in units of system international, so in system international units, I would see the value of R is 8.314 Newton per meter square meter cube per mole per Kelvin. And if meter cube multiplies with per meter squared, what I'll get is meter. So Newton meter, I can replace Newton meter with joules. So the value of R would become 8.314 joule, and all the other units remain the same, per mole and per Kelvin. Okay, and now we have already discussed this in thermodynamics, that 1 calorie equals 4.18 joules. And if I replace joules with calories over here, I'll get the value of R is 1.978 calories per mole and per Kelvin. I hope this is not confusing. for calories, you can remember is 8, 1, then 9, 7, and 8. 1 value is decreasing. 1 value is decreasing. So it is very easy to remember. Now, I think this discussion is enough uh, to discuss the value of R's, values of R. But here I wanted to discuss the density of a gas. What happens to the density of a gas? What is density of a gas? So PV equals nRT. Now we can play with this equation. If I were to break apart this term, that is n, n is the number of moles. So number of moles, for number of moles, we know that it is mass in gram or molar mass. So for I can replace n over here, PV would become mass in gram or molar mass and RT in its place. Now I want to shift this molar mass into this side of the equation. So this side of the equation becomes PMV small m or RT. Okay. Now I want to shift this volume to this side of the equation. Here it is in multiplication. This will go into denominator. So m over v RT. Okay. And mass per unit volume is called density. Density is equal to mass per unit volume. This is the definition of density. So I can replace it. Pm is equal to density RT. And now, what can I do? I want to find density. I can shift this to the left side of the equation, and this will become denominator. RT will come to the denominator of the equation. Pm over RT is equal to D. So you can find density of a gas if you know its pressure and temperature and molar mass. It is very easy to find density of the equation. But what we must remember the density of a gas. If you were given two different gases, okay, and you were to find the density of those two, what was the relation, and ask that what is the relation between the density of those two gases, you will look at their molar masses. Okay, so you see the molar mass of the gas in numerator. So greater the molar mass of a gas, greater will be its density. If molar masses were the same and the calculation were taken at the same pressure and temperature, so then you can tell that their densities would be equal. Now I'm giving you a question. You have to find the density of two gases. The temperature T is equal to 298 Kelvin, and pressure of 1 atm. What are the densities of carbon monoxide and nitrogen dioxide? What is the relation between their densities? 1:2, 3:2, 4:5, or 1:1? You must answer this question in the comments. Okay, you must answer this question. What is the relation between the densities at a certain temperature and pressure? Okay, now another thing. Can you see the relation between the pressure and density of a gas? If the pressure increases, what happens to the density of the gas? The density of the gas also increases. What happens to your temperature? You will see the air of the fan, it does not feel that much in colder, in hotter weather, in warmer days, in hot days. You don't feel the blow of the fan that much. Why? Because the temperature is very high. So the temperature is very high, the density of the gas is very low. So lower density gas is not felt that much. In winter season, you feel it more. Why? Because the temperature is low, the density is high. So higher density air feels more. So this was about it. Now let's come to the discussion of the theory, another theory of gas, that is called kinetic molecular theory. Kinetic molecular theory was put forward by a scientist called Bernoulli, about whom it is said that Bernoulli family had hundreds of Bernoullis, all geniuses. So one of the geniuses of the Bernoulli's family put forward a theory. He said that I must look at my mic because it goes off and then this becomes a problem. Okay, so Bernoulli's put forward kinetic molecular theory, and he said that a gas, I will describe them just orally, not write them down because it takes time. Okay, first of all, he said that all gases consist of small particles called molecules, and those molecules of gases are in random motion. And as long as they collide with certain object, they travel in a straight line. But when they collide with the wall of container, they exert some force on it. And that force, we measure it as the pressure of the gas. So when the particles collide with the wall of container, it exerts some pressure, which we call pressure of the gas. He said that the collision between among the molecules or the wall of container is elastic. No momentum or energy is lost during this collision of the molecule. Another postulate of this theory was that the actual mass of the molecules of the gas is negligible as compared to the volume of the gas. So suppose you have a gas in a container. This is the volume of a gas now, but the actual mass of the molecules of the gas is negligible. And the actual volume of the gas is compared to Vm. So Vg, I'll call this Vg, is very, very, very greater than Vm. Vm means volume of the molecules, actual molecules. So we must neglect the volume of the molecules. So this all space is now available for the gas to go around and enjoy and bump into one another on the wall of container. So this was one of the postulates. So Vm is equal to 0 according to KMT. Another thing, he said that one particle, one molecule of the gas is independent of another molecule of the gas. There is no forces of attraction between the molecules of the gas. So forces of Fa, forces of attraction was equal to 0. There was no bound on the molecule, so they could freely hit the wall of the container and exert some force, and we can see that as a pressure. Then this was, I think, I don't now remember which number was it, but again he said that we see that there is no effect of gravity on these molecules. Their motion is independent of the effect of the gravity. And then he said at the last that there is a linear relationship, a relationship between kinetic energy of the gas molecules and temperature. So the average kinetic energy of the molecules are directly proportional to its temperature, absolute temperature. And this was then, I think, expressed by Clausius, that he said that kinetic energy is equal to 3 by 2 RT for a certain amount of a gas. And from this we can derive the value of Vrms, that is root mean square velocity. We can derive the value of Vrms from this equation, and I will do that. Just first I have to look at my mic. Okay, So kinetic energy equals 1 over 2 mv bar squared, because now I have taken here r for the whole of the gas. Okay, so 3 by 2 RT. What does V bar means? This is mean velocity, squared of the mean velocity. Mean velocity mean I have taken all the velocities up, square of the velocities v1, v2, v3, squared divided by 3. So I have divided the number of the velocities of all the molecules divided by the number of the molecules. So this is the mean squared velocity. Now you must look at this equation. Can 2 cancel with 2? Yes. So here from the left side I can see Vm bar squared is equal to 3RT. Okay. And now I can see that mv bar squared equals RT, or v bar squared equal RT over m, and this m is the molar mass of the gas. Okay. Now I can take square on both sides, and this side square root on both sides, and square root cancels with square root. So this becomes VRMS equals 3 under the root 3RT by M. So this is root mean squared velocity of the molecules. So on the basis of these postulates of Bernoulli's, then different scientists came and explained different behaviors of the gases. Like Maxwell came and explained the velocities distribution of the molecules, and after him came the um, Boltzmann, who was an unfortunate person, very brilliant scientist, but killed himself, killed by suicide. And he came and distributed the energies of the molecules, how much molecules will have how much energies. So that is Maxwell-Boltzmann distribution for velocities and energies. But we saw that the molecules do not behave ideally, as was taken by this scientist Bernoulli's, or different scientists like Boyles and Charles and Avogadro's. We see different behavior in real case scenarios. The theories is different, but the molecules in actual case scenarios behave differently. So van der Waal came and corrected all these equations for the real gases. Now we will discuss the difference between real and ideal. So the main differences, one of them is the volume and the other one is the force of attraction. So Bernoulli's in Kinetic Molecular Theory said that the actual volume of the molecules of gases are negligible, but this is not the case. In another postulate was that forces of attraction are negligible, but this was not the case. Now we will discuss that in detail. Ideal versus non-ideal behavior of the gases, and this will be the last topic of our discussion for today. And we will discuss Z, that is compressibility factor. If I do not forget it, I will discuss Z, compressibility factor, why it comes down, and then so till now we were able to develop a general gas equation that was PV equals nRT. But we found that this was not valid in all cases for all the gases. In high cases for all the gases. What we saw that real gases at high pressure and low temperature would not follow PV equals nRT. And we found that there was a glitch in our premises, like in kinetic molecular theory, we said that the actual volume of the molecules of gases was negligible. So this was one of our premise, like one of the postulates of the kinetic molecular theory, which was wrong. So it made our equation not work in real scenarios. Another thing, we said that there is no force of interaction between the molecules of the gas. So again, we found that this is not the real case scenario. In real cases, we find the molecules interacting with one another. So that because of these two false assumptions, we are finding that in real cases, we are not seeing PV equals nRT. So we will explore that in detail now. The first thing first, they thought that these in ideal situation, we found that we assumed that gas molecules are point masses. Okay, so by point mass, what did we mean? We meant that these molecules, when you combine them together, they do not occupy any uh, considerable space. So you can compress them to a space that is negligible as compared to the volume in which they are moving around. So this means that all the volume, all volume is freely available for the motion of the molecules. Means the volume occupied by the molecules themselves is not worth noticing. So you do not have to give heed to that volume. Means they are not hampering their motion. So what we found in reality, volume of the molecules at high pressure and low temperature was not negligible. So the actual molecules were not point masses, but spheres of masses. Those rigid spheres, they were occupying some space in the volume at low pressure, at high pressure and low temperature. So they were occupying uh, some space in the volume of the gas. So what does this mean? This means now this whole space is not available. The free space for the motion of the molecules is now less than the whole space of the gas. Okay, so suppose this is volume, as in the case here in ideal case we would have the volume V as ideal. This is wholly available for the motion of the molecules. Here this whole volume available, but here we will see that this whole volume is not available for the free motion of the molecule. Some of its space is occupied by the volume of the molecules itself. So there is a difference between the volume of the gas and the volume of the molecules. So what will we find? That actually V ideal, we are not seeing that this whole space is now available for the molecule. In case of V ideal, we had the whole space available for the movement of the molecules. Now these spheres are occupying some space, so we must exclude this volume, the volume of the molecules, to make the aware to find the available freely available volume for the molecules to move around. We must subtract this volume from the total volume of the gas. So this is the total volume of the gas. Suppose we ideal, we must subtract some term, that is excluded volume. And this was done by van der Waals, and he used the term B for the excluded volume. Okay, and he said that this B was equal to 4 times the volume of the molecules. Okay, so this excluded volume is equal to B, which is 4 times the volume of the molecules, these spheres. So for the spheres, we know the formula is 3 by 4 pi r cube. So you can plug that in. You do not need these formulas, etc. But you must know, you must remember that we must subtract some volume, that is the volume occupied by the molecules themselves. In reality, we must subtract this. So we must subtract V from our ideal volume to find the real space available for the molecules to move around. Why did I multiply it? For 1 mole, it must be equal to 1. If I put 1 over here, I'll get V minus B. But for n number of moles, I will get V minus NB. So this is called the volume correction. Volume correction in van der Waals equation. And this is the one faulty assumption and its correction. Okay, another faulty assumption was that we consider in kinetic molecular theory that there is no force of interaction between the molecules. So if there were no force of interaction between the molecules, we would have found the molecules at point masses bouncing into the wall of container independent of other particles around it. So we would have P pressure because of this bouncing to the wall of the container. It is exerting some pressure. We would call this P ideal. But what happens in real case scenario, we are finding the molecule to be slowed down, to be slower down because of the interaction with other particles. Suppose this is my molecule A reaching the wall of container and is about to hit it. But here we are finding other molecules of kind B, suppose, interacting with my molecule A and reducing its speed with which it is going to hit the wall. So it is pushing the molecule which is hitting the wall of the container back. So a push back for this molecule, and this will decrease the pressure. So here, if I am absorbing pressure P absorb, I'm absorbing some pressure. This pressure must be less than ideal. Yes, I found that this pressure was less than ideal. So by how much? By that much, by that amount with which these molecules were attracting this molecule in backward direction. And to this backward attraction, I called it P internal. Okay. And what I found that this P internal was directly proportional to a concentration of these molecules. So this P internal, I call, suppose this P dash, was directly proportional to concentration of these molecules. And another thing I found was it was also directly proportional concentration of this molecule, which is near the wall of the container. So internal directly proportional to concentration. Combining these two, I got concentration squared, n squared over v squared. And to put a constant and remove the proportionality, I put a n squared over v squared. So my I must add this P dash to my P absorbed to make it equal to P ideal. So P ideal would be equal to my P absorbed plus P dash. So P ideal at the end becomes equal to P absorbed plus what is P dash? A by n square over V square. So this is called the pressure correction, van der Waals pressure correction in ideal gas equation. So now we must correct it for the pressure too. And this is the pressure correction. Now I will go to the detail of A and B just a bit. And then we will discuss compressibility factor, and then we will wind up for today. Okay. Now so what are A and B? A and B are van der Waals constant. A and B. Van der Waals constants. Okay, if I were to tell you that B is excluded volume, then you can tell me that B must depend upon the size of the particle. Greater the size of the molecule, greater will be the excluded volume, the volume occupied by that volume, the occupied, the volume occupied by that molecule. So if you were to tell me, suppose CH4, then C2H6, and then C3H8, which one would have a greater value of B? So it is obvious, greater the size of the molecule, greater will be its value of B. So this was about B. About A, uh, what about A? A depends upon, it tells you how much a gas is, how much, it tells you the value of interaction between the molecules. Greater the amount of interaction between the molecules, that is the force of intermolecular force among the molecules, greater will be the value of A. So lesser the value of A, lesser will be the interaction between the molecules. Another thing, so this is directly proportional to intermolecular forces. Okay, so now you can tell me that which one will have greater value of A, a polar molecule or non-polar molecule? Obviously, a polar molecule will have greater value of A. So polar molecule will have greater value of A than non-polar. So you can tell me that NH3 will have greater value of A than H2. Okay, so this is about it. Another thing, A also gives you uh, a hint the about the liquefaction of a gas. Greater the value of A, greater will be the ability of that gas to liquefy easily. So for easy liquefaction, you must have greater value of A. So as SO2 has greater value of A than helium, so it liquefies easily than helium. So this was about A and B. Now let me tell you something about the calculation of units of A and B. So one thing to tell you about A and B is that you must look at with which thing they are adding up or subtracting from. So now I must write the equation, that is van der Waal corrected equation for real gases. So P would be P plus A n squared over V squared into V minus NB equals nRT. Now this is the corrected gas equation. Now here what I want to tell you is if you were to find the value of A, the unit of A, you have to take this whole term. Okay, here I'm clarifying one concept, that if I'm adding up two physical quantities means these both have the same dimensions. So this whole term will have the same dimension as P. So P, here I am equating them both for the dimensions A n squared over V squared. Okay, so I know the units of all these terms in my equation. I know the unit of P, I know the unit of N, I know the unit of volume. So I must plug them in. Here the unit of P I'm putting ATM. Okay, again A in its place. The unit of N is mole. Okay, N squared comes out. The unit of volume is liter, N squared with that. Okay, now we can now we can take the numerator to denominator and do the simple mathematics. Okay, so this becomes ATM, and I have to take this into my from denominator to numerator. Okay, so this becomes letter squared. Okay, again, and here the mole is in numerator. If I bring it to the other side of equation, this comes to denominator of my equation, so mole squared A. As a result, what will I get is the unit will become ATM dot, by dot I mean multiplied, ATM letter squared mole minus 2 inverse, as I brought it from numerator to denominator to numerator. Okay, so this becomes inverse. Okay, what about the units of B? It is very easy. Again, V minus NB. As I said, addition and subtraction. You must have the same dimensions. So I can put the equation because both sides are equal, so I can put equality sign. So for volume, we have the unit of what? Meter cube. Okay, and for N the unit is mole, and B can we find. So mole comes in the numerator, and we can have meter cube mole inverse the unit of B. Hope I was able to clarify the concept. Now we will go to compressibility factor and talk about it. So if a gas was following PV equals nRT, this is very obvious. Let me take that equation. PV equals nRT. If a gas was following this equation, what would happen if I take this hand side of the equation to this hand side? It These all terms would come to the denominator of the equation, and I would get PV equals nRT is equal to 1. And to this I called compressibility factor. I represent it by Z. So if PV equals nRT, I will get 1 from this equation. And for that gas, I will have a compressibility factor equals to 1. So does this happen in reality or not? We will explain this in detail. Let's talk about the compressibility factor. Okay, PV over nRT. Now, if I had an ideal gas, what would I get is a straight line of PV over nRT versus P. If I were to increase the pressure, I would see the decrease in volume. Okay, like I'm increasing the pressure is for Boyle's law. I must have seen the decrease in the volume of equal sort, of equal amount. But here, what I see in reality, in some cases, I see the product of PV not equal to nRT, but less than nRT. What I see the compression more than in ideal case. What by this I mean V ideal would have been greater than V real. In reality, I see a lesser the volume compressing more than it should have been. So if the volume is compressing more than it should have been, means the particles are coming closer than I have predicted. Mean there are forces of attraction among the molecule. Okay. In the other case, if the PV product comes greater than nRT, means the volume is not compressing as much as I have predicted. Here in this case, the volume was compressing more than I predicted. Here the volume is not compressing as much as I am predicting from Boyle's law. So here what I'll see is V real greater than V ideal. Okay, if V real is greater than V ideal, it means there are repulsion among the molecules than attraction. Okay, so forces of repulsion among the molecules. So in reality, I see some gases deviating in positive ways. This is positive of my graph. This is greater than 1, and here it is less than 1. So some gases like hydrogen and helium deviating in positive direction. Some gases first in negative direction, then in positive direction. I'll explain that in a minute too. Why first in negative direction? When you increase the pressure, first, the gases come closer to one another. Molecules come closer to one another, and I see that forces of attraction comes uh, into the play, and the volume compresses more than I have predicted ideally. Okay, but when you increase further pressure, there is no space of interaction, no further space to the for the molecules to compress any further, and forces of repulsion there dominate. So the V real then goes more than V ideal. So I will have PV for PV more than PV. The product of PV would be greater than nRT, and I would have compressibility factor more than 1. One thing to be noted that if there is no force of attraction or repulsion among the ideal gases, so for an ideal gas, if there is no force of interaction, no force of attraction, so you cannot cool them down to liquefy. So they do not liquefy. Ideal gases do not, and you will not see Joule-Thomson effect applying on them. So no Joule-Thomson effect for them. For ideal gases. For ideal gases, you cannot liquefy them and you will not see any Joule-Thomson effect applying on them. So this was all about it. Uh, Ideal versus real. First of all, that the ideal gases, we consider they were point masses, but in reality, we didn't see that. For ideal gas, we saw that PV equals nRT, but for real gases, what we saw that P plus A n squared over V squared, V minus NV equals nRT. Okay, uh, corrected by van der Waals. So this was all the differences. I hope I have clarified them.